Yay!
Yay!
Okay, so now let's talk about the thermal energy stored in objects. For right now, for the next couple of problems, we'll do like liquids and solids. We'll get to the thermal energy of gases probably in the next unit, because that's a little bit different. All right, so we can tackle some kind of interesting problems. So here, let's suppose you've got a backyard swimming pool, and you're lucky enough to have a heated backyard swimming pool, and you're having a party, so you want to heat this pool. Maybe it is, I don't know, 20 degrees Celsius outside. So let's say that the water is the ambient temperature of the air, so we want to go from an initial temperature of, let's say, 20 Celsius, right? That's like, make sure you can do this, 68 Fahrenheit. If you use Fahrenheit, make sure you can convert back and forth. And what we want is to bring the water up to, let's do an easy final temperature. So let's just say 30. We want to bring the water from 20, the ambient air temperature outside, up to 30. And 30 would be, I guess this is sort of a pleasant swimming temperature, 86 Fahrenheit. Okay, so it's going to require some energy to do that. Here's our pool. It's kind of, maybe it's a goofy looking pool, but maybe 10 meters across, so 30 feet by 15 feet, 10 meters by 5 meters. Suppose on one end of the pool, it's 3 meters deep, so, 9 feet, and then there's the baby pool end, 1 meter, like 3 feet deep. Okay, so we fill it up with water. You can tell it's water because that's blue. That's the limit of my artistry. And what we want to do is we want to heat this thing. So it's going to require some energy. How much energy do we need? All right, so what we're going to use is we're going to say the amount of energy that we can store as thermal energy in the water. We're going to put the energy into the water. The amount of energy is just going to be mc delta T. All right, M, that sounds easy. That's just the mass of the stuff you want to heat up. So that's going to be the mass of the water in the swimming pool. We'll find that in just a second. C, this is called the specific heat, for what seems like no good reason. That's a different use of the word specific. Anyway, the units, you can kind of see what the units have to be. U is going to be the amount of energy is in joules. So the specific heat is going to have to be, if you multiply by M and delta T, you got to get back to joules. So this has to be in units of joules per kilogram per degree Celsius, or Kelvin, right? Because 1 degree Celsius is 1 Kelvin. Anyway, it's the energy you need to change 1 kilogram of something by 1 degree. That's the specific heat, and it's different for every substance. Usually this is something you look up in a table or a book or whatever. It's different for every substance. So multiplying all these together is going to tell us how much energy we need. Delta T, we already know that. That's 10 degrees. Right? We're going from 20 to 30. So that, delta T is T final minus T initial. So that's 30 minus 20, 10. All right. So I'm going to need to know the specific heat of water. And the specific heat of water is about 4,200 joules per kilogram degree. So if I'm going to heat up 1 kilogram of water, how much is a kilogram of water? Remember how the metric system works? 1 kilogram is 1 liter. It's cool how that works out. It's kind of defined that way, really. So if you have 1 liter of water and you want to raise it by 1 degree Celsius, you're going to need 4,200 joules to pump into the water in order for that to happen. That's its specific heat. It also goes the other way, by the way. So if water cools, if a kilogram of water cools by 1 degree, it releases. You have to take out 4,200 joules. So it works either way. It's just a measure of how hard it is to heat something up, or how hard it is for something to cool off, how much it keeps its heat. Water has one of the higher specific heats. Metals are much less. It's easy to heat up metal as opposed to water. So metals usually have a lower specific heat than water does. Water is pretty tough. Okay, so now I know the specific heat. I need to know M. What's the mass of the water? Okay, first, let's get the volume of the water. That's going to be a little bit easier. The volume of the water that we're dealing with, let's see, that's going to be 10 by 5 by... Now, how am I going to handle the varying depth? Well, the way that I drew it is pretty simple. So if it smoothly goes from 1 meter to 3 meters in depth, can I just sort of take an average and say that the average is going to be like 2 all the way across? That would be sort of an easy thing to do. So let's just say it's, on the average, it's 10 by 5 by 2 meters. So what is that? That's 100. 100 cubic meters of water. And so to get the mass of the water is just going to be the density of water times the volume. That's how that works. The density of water, what's that? Again, the metric system comes to the rescue. The density of water is 1,000 kilograms for every cubic meter. It's easy. And then I just multiply by my volume, which is 100. So the mass of the water that I'm trying to heat, it looks like that's going to be 100,000, 10 to the 5th kilograms of water. So it looks like I'm all set. So the amount of energy that I need is just going to be 10 to the 5th times C 4200. You can see how the units are all going to work out, and delta T is 10. So when I multiply all these things together, what do I get? It looks like I get 4.2 times 10 to the 9th joules. 4.2 gigajoules, 4.2 billion joules. That sounds like a lot. But, I mean, it's a lot of water, and water is hard to heat up. So somehow I'm going to need to come up with 4.2 billion joules to heat up this swimming pool. The cool thing is that you can get energy from the energy companies. Maybe you have an electric heater or whatever to heat up the water. They're going to charge you money. So originally I want to know, how much is this going to cost? So how much does energy cost? You can look on your bill. You should get a bill every month from wherever you are, from your energy company. Around here, about maybe the middle of the United States, I think we have pretty cheap energy, as far as I understand it. Our energy is about 10 cents per, here's how it's charged, kilowatt hour. We're usually charged in units of kilowatt hours, 10 cents for every kilowatt hour. Okay, you might not have seen a kilowatt hour before. I mean, the SI unit is joules, right? So what is a kilowatt hour in joules? Well, a kilowatt, 1 kilowatt hour. Well, what's a kilowatt? It's 1,000 watts, and a watt is a joule per second. And then I'm going to multiply by an hour, convert it to seconds, 3,600. So that's going to be 3,600 seconds. So there's my joules. So it's 3.6 million joules. Okay, so 1 kilowatt hour is 3.6 million joules, and that's going to cost you 10 cents. Or maybe an easier way to think about it is 3.6 times 10 to the 7th joules per dollar. That's what it's going to cost in order to do this thing. So I think I'm all set. I already know what my energy budget is. I need 4.2 billion joules. I know how much it's going to cost me. Every dollar gets me 3.6 times 10 to the 7th. So if I just divide those two things, then I got it. So 4.2 times 10 to the 9th joules divided by 3.6 times 10 to the 7th joules per dollar. Joules goes away. Dollars flip up to the top. And I think if you do this, you get something like a little more than $100. I think it's $117, something like that, to heat up the swimming pool. That sounds like a lot. And it is a lot. Heated swimming pools are sort of a luxury. Yeah, it costs a lot of energy to heat up a pool. Notice now you can do some neat things. Once you know how much a kilowatt hour is, that's a unit that's used quite a bit, especially more and more in the modern day. Like electric cars, their batteries are rated in kilowatt hours. So like a Tesla Model Y, I looked it up. Tesla Model Y, newer electric cars, their batteries are rated for 75 kilowatt hours. That's how much energy they can store. 75 kilowatt hours, every kilowatt hour is about 10 cents. So to fully charge a modern electric car like a Tesla from a home here in the middle of the United States, well, it's 75 kilowatt hours. Each one is 10 cents. So it's going to cost you a little more than $7 to go from 0 all the way up to a full battery. And that'll get you, what, like 300 miles of range, something like that. So yeah, that's somewhere between a half or a third as much as it would cost you to fill up with gas. So that's one reason that some people switch over to electric cars. Cool. So now you can do all sorts of neat problems with kilowatt hours, the cost of power or the cost of energy, and electric storage.